Cosmic tunnels or sci-fi dreams? Kip Thorne unravels wormholes. Imagine a shortcut through the cosmos, a tunnel bending the fabric of space-time to connect distant stars or even different times, defying the vast distances of our universe. This is the allure of wormholes, theoretical passages first proposed in 1916 and brought into the scientific spotlight by physicist Kip Thorne, whose work on Interstellar grounded these sci-fi staples in real physics. In his book The Science of Interstellar and numerous talks, including a pivotal discussion with Neil deGrasse Tyson on Star Talk, Thorne explores whether wormholes are real or mere mathematical curiosities. Rooted in Einstein's general relativity, wormholes are solutions to equations describing space-time, yet their existence hinges on exotic matter and quantum mechanics, with no direct evidence to date. In 2025, as telescopes like JWST probe cosmic mysteries, Thorne's insights, sparked by a 1985 call from Carl Sagan, continue to fuel debates about cosmic highways and time travel. Join me as we dive into his explanations, unpacking the science, challenges, and tantalizing possibilities of wormholes in 10 gripping paragraphs. Wormholes, formerly known as Einstein-Rosen bridges, emerged from Einstein's 1916 general relativity equations, specifically as solutions linking 2 points in spacetime via a tunnel-like structure. Kip Thorne, the Feynman Professor of Theoretical Physics at Caltech, revitalized their study in the 1980s, inspired by Carl Sagan's novel Contact, where he needed a scientifically plausible way to transport a protagonist 26 light-years to Vega quickly. Thorne proposed traversable wormholes, unlike the non-traversable bridges theorized earlier, which collapse instantly. These tunnels connect two distant regions, or potentially times, through a higher dimensional throat, allowing near-instantaneous passage, as if folding a piece of paper to bring 2 points together. Thorne's 1988 paper with Michael Morris formalized this, showing that a wormhole could remain open with exotic matter possessing negative energy density, defying classical physics but permitted by quantum mechanics. His work, detailed in Black Holes and Time Warps, sparked serious scientific inquiry into whether such structures could exist naturally or be engineered, transforming wormholes from mathematical oddities to potential cosmic phenomena. The theoretical foundation for wormholes rests on general relativity, where space-time curves under mass and energy, allowing topologies like tunnels through a higher dimension. Thorne explains that a wormhole has two mouths connected by a throat, with an object entering one mouth emerging from the other, even if separated by trillions of miles. For example, a spaceship entering a wormhole near Earth could exit near Alpha Centauri, bypassing light's speed limit in normal space. However, Thorne emphasizes that without exotic matter, wormholes collapse faster than light can traverse them due to gravitational instability. Exotic matter, with negative mass or energy, counteracts this by generating repulsive gravity to hold the throat open, a concept rooted in quantum field theory's Casimir effect, where negative energy arises between metal plates. Thorne's calculations, inspired by Sagan's query, showed this is theoretically possible, but no such matter has been observed in quantities sufficient to stabilize a macroscopic wormhole, making their natural existence speculative. Thorne's exploration of traversable wormholes, detailed in his 1988 paper, hinges on exotic matter's hypothetical properties, which challenge classical intuition but align with quantum mechanics. Negative energy, briefly produced in lab settings via quantum fluctuations, could theoretically stabilize a wormhole's throat against collapse, but Thorne cautions the amounts needed are astronomical, potentially requiring the mass energy of planets converted to negative form. He notes that quantum foam, a sub-Planck scale froth of spacetime fluctuations, might host microscopic wormholes, but scaling these to human traversable sizes is daunting. In The Science of Interstellar, Thorne explains that naturally occurring wormholes are unlikely, as stars collapsing into black holes are common, whereas no cosmic process is known to form wormholes. He speculates that an advanced civilization with unlimited resources could construct one, but this remains science fiction, as evidenced by 2025's lack of observational hints from telescopes like the Event Horizon Telescope, which images black holes but finds no wormhole signatures. Time travel through wormholes is another tantalizing possibility Thorne explores, particularly in discussions with Neil deGrasse Tyson on Star Talk. By manipulating a wormhole's mouths, one placed near a massive object like a black hole where time flows slower due to gravitational dilation, the mouths can desynchronize. For instance, if one mouth orbits a black hole for hours while the other remains on Earth for 1 billion years, entering the Earth-side mouth could propel you back to the black hole's era. Thorne's excitement, shared with his Caltech students, was tempered by a grim realization. Quantum gravity effects like vacuum fluctuations cause wormholes to self-destruct when used as time machines, a mechanism he dubbed a universal kill switch to keep the universe safe for historians, as Stephen Hawking quipped. This instability, driven by infinite light amplification at the Cauchy horizon, suggests time travel wormholes are physically implausible with current physics, a point Thorne concedes despite their mathematical validity. This instability, driven by infinite light amplification at the Cauchy horizon, suggests time travel wormholes are physically implausible with current physics, a point Thorne concedes despite their mathematical validity. Thorne's work on Interstellar brought wormholes to public imagination, ensuring scientific accuracy in depicting a traversable wormhole for interstellar travel. Collaborating with Christopher Nolan, he crafted a visually stunning wormhole based on Einstein's equations, with equations scribbled on blackboards reflecting real physics. The film's wormhole, a sphere rather than a 2D hole due to gravitational lensing, allows astronauts to cross galaxies, a scenario Thorne deems feasible only with exotic matter or alien engineering. He notes that while black holes have observable signatures like accretion disks seen by IXPE in 2025, wormholes lack such evidence, remaining theoretical. Thorne's role as executive producer ensured the film balanced speculation with science, inspiring awe while highlighting the absence of empirical wormhole detections, even as JWST's 2025 exoplanet data fuels cosmic curiosity. The stability problem is a major hurdle, as Thorne explains in Black Holes and Time Warps. Even with exotic matter, wormholes are prone to collapse from perturbations like a spaceship's passage, with tidal forces akin to black holes' spaghettification potentially shredding travelers. Quantum vacuum fluctuations amplify catastrophically, pinching off the throat, as Thorne discovered with students, making human-scale wormholes impractical without exotic stabilization mechanisms unknown to current physics. Hypothetical dark energy, with negative pressure, might stabilize them, as Stephen Hawking and collaborators suggested, but its macroscopic use remains unfeasible. Thorne's cautious optimism contrasts with sci-fi's optimism, noting that 2025's gravitational wave observatories like LIGO detect black hole mergers but no wormhole-like signatures, reinforcing their elusiveness. Wormholes' potential as cosmic shortcuts captivates Thorne, who sees them as mathematically sound solutions to Einstein's equations, as noted in a 2025 Yahoo article. Unlike black holes, which trap matter at singularities, wormholes offer two-way portals, theoretically enabling faster-than-light travel relative to external space-time, though not violating relativity locally. Thorne's work with Sagan on Contact replaced hyperspace with wormholes, avoiding singularity's destructive reign of ultra-relativistic matter. Yet he stresses no natural formation mechanism exists, unlike black holes born from stellar collapse, and 2025's lack of anomalous gravitational lensing or energy bursts keeps wormholes hypothetical despite their appeal in science fiction like Battlestar Galactica. Quantum gravity poses another challenge, as Thorne discusses with Tyson, noting that theories like string theory or loop quantum gravity might allow microscopic wormholes in quantum foam but not macroscopic ones. String theory's extra dimensions could host stable wormholes, but scaling them requires energy scales far beyond current technology, as 2025 quantum gravity simulations confirm. Thorne's work inspired ADS-CFT correspondence studies, where wormholes link entangled black holes. But these remain theoretical, untestable, with present instruments like CERN's upgraded LHC, leaving wormholes' reality uncertain. Thorne's legacy lies in making wormholes scientifically respectable, as seen in his Nobel Prize-winning contributions to gravity and Interstellar's impact. He cautions that while mathematically possible, their existence depends on physics we don't fully grasp, like quantum gravity's role in stabilizing exotic matter. 2025's observational landscape, EHT's black hole images, LIGO's mergers, shows no wormhole evidence, but Thorne remains open to surprises, as cosmic anomalies could hint at their presence. In conclusion, Kip Thorne's work reveals wormholes as tantalizing but unproven, grounded in relativity yet demanding exotic physics. Their reality hinges on future breakthroughs, but for now, they inspire awe and inquiry, bridging science and imagination. If wormholes spark your curiosity, share your thoughts. Could they be out there or just cosmic dreams? Stay tuned for the universe's next twist.